In this topic, we're going to look at solving travelling salesperson problems. We're going to use two algorithms for this, one to find an upper bound and one to find a lower bound for the optimum route. A travelling salesperson problem is one in which you want to start at a vertex, visit every other vertex exactly once and return to the start in the shortest distance possible. This is a different problem from the route inspection problem we looked at earlier with the Chinese postman algorithm, where the aim was to travel along every edge exactly once. Recall from the definitions at the beginning that a cycle that visits every vertex of a graph is called a Hamiltonian cycle. So we are trying to find the optimum Hamiltonian cycle for the network. There isn't an algorithm that will find this optimum cycle for us. However, there are two algorithms, one which will find an upper bound, which can be thought of as a worst case scenario, and another which will find a lower bound, which is a best case scenario. So that then gives us two bounds in which the actual answer lies between. So we're going to try to find a Hamiltonian cycle for this network with the smallest possible total weight. So by inspection, we could start at vertex A, travel to E, D, B, C, and then back to A. This would give us a tour of total weight 40. Any closed walk like this that visits all of the nodes in a network is also called a tour. A tour of this type will always give us a possible solution, but it might not be the minimum. There might be a tour that is shorter than this. That is why any tour can be thought of as an upper bound or a worst case scenario. The smaller the value of the upper bound, the better it is. There is no algorithm to find an optimum Hamiltonian cycle. However, what we can do is we can find bounds on what the solution may be. The nearest neighbour algorithm will help us to find a Hamiltonian cycle. It may not be the best Hamiltonian cycle, but because it definitely works as a solution, it can be thought of as an upper bound. The first step is to start at the first node. We're going to start at A in this case, and we're going to choose the smallest arc connecting to a new node that has not been visited yet. So from A, we would choose to go to E with a length of 8. From there, we then need to travel to another node which has not yet been visited, and again choose the arc of smallest weight. So in this situation, we're going to pick B, so E to B, which has got a weight of 7. And we're going to continue in this way until we have visited all of the nodes. And once we've visited all of the nodes, we'll return to the start. So we'll go B to C, C to D, and D to A. We've written down the tour as A, E, B, C, D, A, and given it a total weight of 48. So this might not be the optimum Hamiltonian cycle, but it is definitely an upper bound. And if we can find several upper bounds, we can then choose which is the smallest, and the smallest upper bound will be the best one. So having started from node A, we have got this tour here, A, E, B, C, D, A, with a weight of 48. We can now repeat the nearest neighbour algorithm, starting at the other nodes, to see if we get a different answer. So starting from B, choosing the shortest arc each time before returning to the start, the nearest neighbour algorithm gives us the tour B, C, A, E, D, B. That has a weight of 45. So already that is a better upper bound than the one we previously had. Starting from C, the nearest neighbour algorithm produces the tour C, B, E, A, D, C. also with a weight of 48. Starting from D, we get the toe D, B, C, A, E, D with a weight of 45. And starting from E, we get E, B, C, A, D, E with a weight of 49. So of these 5 toes, which is the best upper bound? Well, the smallest number is the better, because these are all worst case scenarios. So 45 will be the upper bound that we will choose. Why is this an upper bound? Because it's a toe, it definitely works, it definitely could be a solution, but potentially it could be improved upon. We're now going to look for an algorithm that will find a lower bound for the optimum Hamiltonian cycle. So we're going to consider a cycle with 6 vertices and 6 edges, and we're going to look at how that cycle is made up. So this could be a Hamiltonian cycle with the vertices joined in a cycle as shown. And we're going to consider deleting one of the vertices and the edges associated with it. So whichever vertex we deleted, we would also have to delete 2 edges. We're going to delete vertex D, and along with it, the edges DB and DF. I'm going to consider what is left when we do that. So the type of graph that is left when we do that is a tree. It's actually a straight line, B to A to C to E to F, but it is a special kind of tree. So what we can conclude from that is that a cycle is made up of 2 elements. It's made up of a tree and a vertex that isn't part of the tree and 2 edges joining to that vertex. So if we want to make a lower bound, our lower bound is going to consist of 2 edges from a particular vertex and a tree that joins all of the remaining vertices to each other. So this is the lower bound algorithm for finding the optimum Hamiltonian cycle. The first thing we need to note is that this algorithm will not necessarily find us a toe. What it will do is it will give us a number below which there definitely doesn't exist a toe of that value. So whereas the nearest neighbour algorithm actually gave us a toe, it might not have been the best one, but it definitely created a toe. This algorithm will just give us a number below which no toe can exist. It might create a toe, but not always. So here's a network. We're going to start by choosing a vertex, a node. In this case, we're going to choose node A, and we're going to choose 2 arcs coming from A, because any Hamiltonian cycle will have to include 2 arcs that go through A. We're going to choose the 2 smallest because we're trying to look for a best case scenario. So the 2 smallest arcs are AE and AD. So the lower bound is going to include those 2 arcs. We're then going to delete vertex A and those 2 edges, AE and AD. We're also going to delete any other edges that go from A. We're now going to consider just the 4 vertices apart from A and just the edges associated with those. And we're now going to look for a tree that connects those 4 vertices together. To do that, we can either use Prim's algorithm or Kruskal's algorithm to find the minimum spanning tree. Kruskal's algorithm gives us BC, BE and BD, as the 3 arcs in the tree. We're going to add the weight of these 3 edges onto the 2 initial arcs that we chose that went through vertex A. And combining those 5 edges together will give us a best case scenario or a lower bound. In practice, this may not give us an actual toe, but it gives us a number below which a toe cannot exist. So 39 would be a lower bound for the solution. Notice that in this case, the lower bound algorithm did not find us a toe. So the 2 edges from A to E and A to D, and the tree with the remaining vertices, BE, BD and BC, when put together, do not give us a cycle. What it has given us is a lower bound. So the lower bound we have found is 39. It may be possible to find a better lower bound. A better lower bound is a higher value. This could be found by starting with a different vertex instead of A. If we were to use the nearest neighbour algorithm starting from A, we would get an upper bound of 43 for this network. This would be by going A to E to B to C to D and back to A. So although the lower bound algorithm didn't find a toe, we now have an upper bound, which is 43, and a lower bound, which was 39. We do not know what the best toe is, but we can now write an inequality to show where the solution will lie. So the optimum toe will be greater than or equal to 39 and less than or equal to 43. If the upper bound and the lower bound were the same number, this would mean that we had definitely found the best possible toe. Let's look back again at the nearest neighbour algorithm for finding an upper bound and see what problems might occur. So we're going to start with this graph here. I'm going to start at node A. So the nearest neighbour algorithm would take us from A to B, then from B to C, from C to D, D to E, E to G, and the first problem we encounter is that at this point we have no choice but to travel along GF, which is a very high weight. The second problem we encounter is that now that we are at node F, there is no way of returning to A without first going through C, and C has already been visited. So we will travel through C to get back to A. So 2 problems that could occur. One is that if the graph is not a complete graph, it may not be possible to find a Hamiltonian cycle. You may need to return to one node more than once. Another problem is that this is what is known as a greedy algorithm, which doesn't think ahead, it only thinks what the best solution is for the next step. So you may find that you end up having to go along a particularly heavy edge, such as G to F, because there are no other choices. So by inspection, it may be possible to find an improved upper bound. In this case, for this graph, this is actually a better solution. It does involve a multiple edge going along E to G twice, but it gives a lower value. Now complete exercise 2.3 on page 38.